GOH2. Okay. Double check me, make sure I did all that right. Sometimes I can mess things up, but that is, I think, how that one should be worked. So, okay, let's look at some other things from chapter 6. Not only did we talk about what a mole is and Avogadro's number, but we also talked about mole ratios. So what is a mole ratio? First off, a mole ratio is the number of moles between two compounds if you look at a balanced chemical reaction. So it's essentially, we get a mole ratio from looking at the coefficients in a balanced chemical reaction. For example, if we have this reaction right here, I know that hydrogen and nitrogen, they're both diatomic molecules, can react together to make ammonia, NH3. So if we balance this, put a 2 here, and then we're going to need a 3 here, and I think we're balanced. If we wanted a mole-to-mole ratio between hydrogen and ammonia, what this reaction says is that for every 3 moles of hydrogen that we invest, we will produce 2 moles of ammonia. Okay, so that would be our mole-to-mole ratio. Anytime we're doing this fancy word called stoichiometry, where you're given information about one reactant or product, and you want to know information on another reactant or product, you have to use a mole-to-mole ratio for those two compounds or items in the chemical reaction. So a good example problem for you to go work is 6.56 on mole ratios. You can also, again, always refer back to lecture notes from that chapter. All right, here is another problem from chapter 6 that I just thought would be a good one to work. It says the principal component of kidney stones is calcium oxalate, CaC2O4. A kidney stone recovered from a typical patient contains 8.5 times 10 to the power of 20 formula units, or a fancy word for molecules. 8.5 times 10 to the power of 20 molecules of calcium oxalate. How many moles of calcium oxalate are present in this kidney stone, and what is the mass of the kidney stone in grams? Okay, this problem doesn't use mole ratios, okay, but it is more practice with the kind of stuff we were doing up here. So we'll do it really quick. And we'll have to use Avogadro's number, I'm pretty sure. So we're going to start with the number given right here, 8.5 times 10 to the power of 20 molecules. 8.5 times 10 to the power of 20 molecules of, I'm gonna zoom in actually so that I write smaller. I can tell I'm gonna need to write small. Okay, 8.5 times 10 to the power of 20 molecules of calcium C2O4 oxalate. Okay, and the question says how many moles first of calcium oxalate are present, and then how many grams. So how do we go from molecules to moles? How do we go from molecules to moles? We have to use Avogadro's number. Okay. Remember, molecules are like a number of items. So there are 6.022 times 10 to the power of 23 molecules, no matter what substance you're talking about, in 1 mole of that substance. And that applies to calcium oxalate. So we're going to write this so that molecules cancels out. Molecules, and then we'll write 1 mole of calcium oxalate on top. So molecules cancels. So now we have moles. So then we would just calculate this. So what is that? 8.5 times 10 to the power of 20 divided by 6.022 times 10 to the power of 23. And I got 0.0014 moles of calcium oxalate. Okay, so that answers the first question. So here we had to use this relationship that relates Avogadro's number of atoms, here the atoms were molecules, to 1 mole of the substance. Now we're going to convert moles to grams. How do we do that? Well, we need a molar mass. Anytime you want to go from moles to grams or grams to moles, you have to use molar mass. It's the only thing that relates grams and moles. So we need the molar mass for calcium oxalate. So let's calculate that really quick. We have 1 mole of calcium atoms. And I'm going to draw a wavy line because we're working beneath this here. If we look at the periodic table, which you will have for the exam, that weighs 40.078 grams. We also have 2 moles carbon atoms. That weighs, let's do 12, we'll do 12.011 times 2, so 24.022. And then we have 4 moles of oxygen atoms. So we do 16 times 4 is 64. We add all of this up. I think we can do this one in our heads. $128.1 grams. That's what I got. Equals 1 mole. So that is the molar mass. So we're going to take this number of moles from our first answer, 0.0014 moles. Let me erase. Oh, this should be a 4. 0.04. And now we're going to use the molar mass we calculated and convert to grams. So for every 1 mole, I'm going to write that on bottom because I want it to cancel, we get 128.1 grams of calcium CaC2O4 oxalate. So we do 0.0014 times 128.1, and I got 0.1, if we round, 8 grams. So that is the mass of a typical kidney stone, 0.18 grams. Okay, I'm glad it's not bigger than